So in a moment, we'll see how to actually make an image. But first of all, the very first job of a telescope is simply to collect and concentrate the light. And we'll see in a moment why that explains why telescopes are so big. But let's have a little look at how a telescope works. So very, very simply, we've got a big primary mirror. It's got a hole in the middle in a typical telescope, and we'll see why in a second. Up here we have the so-called secondary mirror. Light is coming down from the sky. It reflects from the primary mirror onto the secondary mirror, and then again down through the hole in the mirror and comes to a focus here. That's where we place our detector, for example, a CCD camera. Now, the CCD detector may be quite small, but the amount of light we get is determined by the size of the mirror, not by the size of the CCD. To understand why this is important, let me draw a different picture. Last week we saw how stars are very faint because the light from a star spreads out as it moves out from the star in concentric spheres, and so the light is gradually spread over a larger and larger spherical surface until when we're a long way away here at the Earth, those wave fronts are almost parallel, and here is the mirror of our telescope catching the light. Now, if you have a bigger mirror, you catch a larger fraction of the light coming from that star. So the amount of light we get is proportional to the area of our mirror, which is likewise proportional to the square of the diameter of the mirror. So a mirror that's twice as large will catch 4 times as much light. Engineers tell us that to make a telescope with twice as big a mirror diameter, in order to pay for the bigger telescope, the bigger building, all the supporting infrastructure, it costs about 8 times as much. It goes as the cube of the diameter. So big telescopes are very expensive. Also, bigger telescopes present more severe engineering problems. Both the telescopes and the mirrors tend to bend more as they get bigger. Gradually, during the course of the 20th century and the 21st century, we've mastered those engineering problems so we can build bigger and bigger telescopes. Another problem with big mirrors is that they tend to bend under gravity as you tip them in different directions. We solved that problem during the 1990s and 2000s. The secret was to push the mirrors back into shape as you tip them around. And there's 2 ways of doing that. One is to have a segmented mirror made up of many separate sections that you can move independently. That was what was done with the Keck telescope in Hawaii. The other way is to make a very thin mirror which you put rods behind and push at to push it back into shape as you tip it around the sky. And that was what was done with the very large telescope built by the European Southern Observatory in Chile. The result is that we now have telescopes that are 8 to 10 meters across. Okay, so how do we make an image? A telescope is really just a camera, very much like this one here. So a camera is fairly simple. We've got a lens. The light comes through the lens and is focused onto a detector at the back of the camera here. So a telescope is really just the same. Now, sometimes when you think of a telescope, you think of a sailor's telescope, and that's got an eyepiece as well. But the reason for that is that the eye is also a camera. It's a lens and a detector, which is the retina. And the job of the eyepiece is to straighten out the light again so that the eyeball can focus the light on the retina. But when we're using an astronomical telescope, we don't look through it, we just record the image. So it's really much simpler. There's no eyepiece, it's just a camera. Now, with an astronomical telescope, we use a reflecting mirror, not a lens. That's because giant lenses would be much too thick and various other reasons. But I'm going to draw it as if it's a lens because it's easier to draw. So imagine we have a lens here, and the light is coming in here, and it's brought to a focus here. So that's the basics of what we're doing. Now, imagine we have light coming from a different direction in the sky at a different angle. So here's some other light coming in here. So that's also brought to a focus, but at a slightly different spot on a flat region here that we call the focal plane. So different regions, different directions on the sky are mapped onto physically different locations on the focal plane. So that's where we put our detector and it records an image. So if we have some weird shape here, that weird shape is duplicated in miniature on the detector. That's what an image is. Different lenses have a different focal length. So some might have a short, stubby focal length. Some may focus a larger distance away. Now, for a difference in direction, this will make a small spread and this makes a larger spread. So the fineness of scale of the image we get depends on the focal length of the lens or mirror in a normal astronomical telescope. So a longer focal length means the light is more spread out, we get a finer scale image. That's why Victorian telescopes, mid-20th century telescopes, tended to be long tubes. So how do we keep our pictures sharp? There are three different effects that can blur our otherwise perfect pictures. The first one is diffraction. Now this is an inescapable physical effect that will happen with any optical system, any lens or mirror. Light waves reflecting from different parts of the mirror interfere with each other as they arrive at focus and leaves you with some net blurring. Now physics tells us that effect is worse for longer wavelengths and it's also worse for smaller mirrors or lenses. So if we, for the moment, if we just stick with visible wavelength light of, let's say, 500 nanometers wavelength, then, for example, let's look at the human eye. So the pupil of the eye is about 5 millimeters across, and that has diffraction blurring of about 25 arc seconds. Now, 25 arc seconds is the perceived size of a human head at about 1 kilometer away. So that's the best you can possibly resolve. If you had a larger telescope, if you had a telescope 1 meter across, then in principle, that could give you a blurring size 1/10 of an arc second across, much smaller. Unfortunately, we don't normally get that lovely 10th arc second resolution because of the second factor, which is atmospheric blurring. So as the light comes down through the atmosphere, refraction from different parts of the atmosphere makes the wavefronts jiggle about, and if you take a very fast movie, as you can see in this example movie here, the image of a star actually waggles about. This twinkling is what astronomers refer to as seeing. Averaged over time, that will make a blurring that's much worse than diffraction. In a typical site like Edinburgh, it might be several arc seconds across. Even on a good mountaintop observing site, it's about 1 arc second across. So how do we get round that atmospheric blurring? Well, there's two ways. The first way is that we can get rid of the atmosphere, we can launch our telescope into space, like with the Hubble Space Telescope. And the Hubble Space Telescope does indeed get that 10th arc second resolution and make beautifully sharp pictures. The other way we can do it is to watch a bright star in the sky as fast as we can and track the image motion that it's making and try to correct for that with optics that we can bend in fast time to counteract that image motion. And that's known as adaptive optics. So now there's one more type of effect which blurs our pictures, and that's optical imperfections. Now, any optical system is never going to be perfect. Then, to get perfect imaging at all angles, for all mirror sizes, for all temperatures and so on is actually physically impossible. So in the design you have to compromise and optimize at some chosen set of parameters. However, if you have errors in your design, or there's imperfections in the smoothness of the mirror, or its shape isn't quite right, then you're only going to make things worse. So for example, the human eye, which as I said in principle can give diffraction limited resolution of 25 arc seconds, it suffers from what's known as spherical aberration. The imaging is imperfect, and in fact our eyes can resolve about 1 arc minute, about 60 arc seconds. Likewise, as some of you may have heard, the Hubble Space Telescope, when it was first launched, had an imperfection in the shape of its mirror, which was not quite right by the order of a millimetre or two. But the result was that it did not get that 10th arc second resolution. Now that was fixed by launching up on the space shuttle some corrective optics, which was put into the light path before the detector. So that was a very expensive fix. But it was worth it. As you can see in this picture I'm showing you here, it did make a dramatic difference to the quality of the imaging by the Hubble Space Telescope. So how do we get that colour information that Catherine referred to? Well, what I have here on this light box is a colour image of the Orion Nebula, where new stars are being formed. Now, the way that a colour image like this is actually made is it's made up of separate components added together. It's really a blue image, a red image, and a yellow image, and they're added together to make the pretty colour picture. But as astronomers, we want these three images, or similar narrower waveband images, separately. We want a blue image, we want a red image, we want a yellow image, and for each one of those, we do that, by the way, we have a filter we place over the top of the detector that's not so different. There'll be a blue filter, a red filter, and a yellow filter, something which restricts the range of wavelengths hitting the detector. And we take one image at a time, and for each one of those, we then simply have numbers around our detector, so we can measure the brightness of a given star in the red, in the blue range, in the red range, and in the yellow range. And the way we get at the physics is to take the ratios of those numbers. Okay, we take the ratio of the blue to the red, and then there'll be some physical prediction from theory about what those numbers ought to be. For instance, in most normal stars, the ratio blue and red will tell us the surface temperature of the star.